Hello and welcome to the GameWise. Tonight, we're going to drift toward the quietest, darkest, and most fascinating objects in the cosmos, black holes. From the silent collapse of dying stars to the gentle warping of time itself, tonight's journey is all about the invisible anchors of the universe, places where the rules of reality as we know them seem to bend and break with silent, graceful power. I'll do my best to keep things soothing and steady, but fair warning, the universe is pretty fascinating. I hope this video isn't so interesting that it keeps you wide-eyed and alert, but if it does, well, at least you'll drift off a little wiser than before. Before we begin our gentle descent into the cosmic dark, if you enjoy this kind of calm, curious content, I'd be truly grateful if you could tap the like button and consider subscribing. It helps this little corner of the internet stay cozy and curious. And if you feel like sharing, let me know where in the world you're listening from and what time it is for you right now. I always love seeing how far that we travel. Now settle in. Let your breath slow. Let the day's thoughts float gently away. Tonight, we're going to explore why space-time curves, why stars die, and what it might be like to stand at the edge of forever. Imagine the universe is a vast, flat, rubber sheet, stretched out perfectly tight and smooth in every direction. This sheet is space-time, the fundamental fabric of reality, a combination of the three dimensions of space and the one dimension of time woven together. Now imagine placing a small marble on it. It makes a tiny dimple, a subtle indentation you can barely see. That's a small planet, like Earth. Now, place a bowling ball in the middle. The sheet sags deeply, creating a significant curve around it. That's a star, like our sun. The planets in our solar system aren't being pulled by some invisible rope. They're simply rolling along the curve in spacetime created by the sun's immense mass. This is the heart of Einstein's theory of general relativity. Gravity isn't a force in the way we usually think of it, like magnetism or a physical push. It is simply the shape of the universe. Matter tells spacetime how to curve, and that curve in spacetime tells matter how to move. It's a beautiful, elegant, and continuous dance. Everything with mass creates a dip, a cosmic well. Your own body, as you rest right now, creates a gravitational well. Though it's so infinitesimally small, it has no noticeable effect on the world around you. Your bed, the building you're in, the entire planet, each contributes to this grand, layered landscape of gravitational curves. We live our lives in this invisible topography, like ants walking on a rumpled blanket, feeling the dips and rises as forces that guide our every step. A black hole is what happens when you place something on that rubber sheet that is so heavy, so impossibly dense, that it doesn't just create a dip, it punches a hole clean through. It creates a well so deep that the sides become perfectly vertical, an inescapable pit in the fabric of reality. A well from which nothing, not even a beam of light moving at the fastest speed the universe allows, can climb out. All of our understanding of black holes begins right here, with this simple yet profound idea, that gravity is geometry, and a black hole is geometry at its most extreme and unforgiving. If gravity is a gentle slope and a star is a deep well, then what creates the bottomless pit of a black hole? The answer lies not in creation, but in collapse. It lies in the death of giants. Imagine a star many, many times more massive than our sun. For millions, perhaps billions of years, it lives its life in a state of perfect, elegant balance. Deep in its core, two colossal forces are locked in a cosmic arm wrestle. The first force is gravity, the star's own immense mass constantly trying to crush it inward, to pull every atom toward the center. It is a relentless, steady pressure. The second force, fighting back with equal strength, is the outward push of nuclear fusion. In the star's core, the heat and pressure are so intense that atoms of hydrogen are slammed together to form helium, releasing a tremendous amount of energy in the process. This energy, this light and heat, radiates outward, pushing against gravity's inward pull. For most of a star's life, these two forces are in equilibrium. The star is a stable, glowing sphere of gas, held in a delicate truce with itself, but this balance cannot last forever. The star is burning through its fuel. Eventually, the hydrogen in the core runs out. Fusion falters. The outward push weakens. Gravity, which has been patient for millions of years, begins to win the arm wrestle. The core starts to collapse under its own weight. For a star the size of our sun, this collapse is eventually halted by other quantum forces, and it ends its life as a quiet, dense remnant called a white dwarf, a glowing ember in the cosmic graveyard. But for the true giants of the universe, the stars more than 20 or 30 times the mass of our sun, gravity's victory is absolute and catastrophic. The core collapses so completely, so violently, that nothing known in physics can stop it. The star implodes in a fraction of a second. This implosion triggers a rebound explosion of the star's outer layers, an event so powerful it's called a supernova. For a few weeks, this single dying star can outshine its entire galaxy, releasing more energy than our sun will in its entire 10 billion year lifetime. What's left behind is the crushed, compressed remnant of the core. It's a place where a vast amount of matter has been squeezed into an infinitesimally small space. It's like taking a mountain and crushing it down to the size of a single grain of sand. The gravity of this tiny, hyperdense object is so immense that it breaks the rubber sheet of space-time. A black hole is born not from something new being added to the universe, but from a star failing to hold itself up against its own weight. It is the ghost of a star, a monument to gravity's ultimate triumph, a quiet, dark remnant of a life lived in brilliant, shimmering light. If you were to take a journey in an imaginary, perfectly safe spaceship toward a black hole, the first thing you'd notice isn't the black hole itself, but the strange, invisible boundary that surrounds it. This boundary is the event horizon, and it's one of the most profound and mysterious concepts in all of physics. It isn't a physical surface. You wouldn't bump into it. It's not made of fire or rock or any kind of matter. The event horizon is simply the point of no return. Imagine a calm, wide river that flows gently at first, then gradually picks up speed as it approaches the precipice of a massive waterfall. Far upstream, a skilled kayaker can paddle around freely, even against the current. But as they get closer to the waterfall, the water moves faster and faster. There's a precise line in the river where the water is flowing so swiftly that no matter how hard the kayaker paddles, no matter how powerful their engine, they cannot escape being pulled over the edge. The event horizon is that line for space-time. It is the boundary where the gravitational pull of the black hole becomes so overwhelmingly strong that the escape velocity, the speed you would need to get away, becomes greater than the speed of light. And since nothing in the universe can travel faster than light, anything that crosses the event horizon is trapped forever. From your safe vantage point far away, you could watch a probe fall toward the event horizon. You would see its light becoming stretched and reddened, its signal taking longer and longer to reach you. You would see its clock, relative to yours, ticking slower and slower as gravity intensified. As it got closer and closer to the edge, it would seem to freeze in time, its image fading into a dim, ghostly red outline that would appear to linger at the brink for an eternity, never quite crossing. But from the perspective of the probe itself, the experience would be quite different. It would feel no bump, hear no alarm. It would cross the event horizon in a finite amount of time, noticing nothing particularly special at that exact moment. It would be like floating over the edge of that cosmic waterfall, the gentle transition from a world of possibilities to a future with only one inevitable destination. The event horizon is a one-way door in the universe. Information can go in, but it can never come out. It's the ultimate boundary, a silent, invisible sphere that separates our familiar, observable universe from the deep mystery that lies within the black hole's final grasp. It is the shore of a cosmic ocean from which no traveler, not even light, ever returns. What lies at the very center of a black hole, past the point of no return, at the bottom of the gravitational well? Our current understanding of physics, based on Einstein's theory of general relativity, points to something so strange, so alien to our everyday experience, that it almost defies imagination: the singularity. If the event horizon is the edge of the cosmic waterfall, the singularity is the single infinitesimal point at the bottom where all the water, all the matter, all of space-time itself crashes together. It is the place where all the mass of the collapsed star, a mass potentially millions of times greater than our own sun's, is crushed into a region with zero volume, a point of infinite density. Imagine taking every book in every library in the world with all their pages, words, stories, and knowledge, and crushing them down until they occupy a single dimensionless mathematical dot. That gives you a sense of the immense compression at play. The singularity is a place where our familiar laws of physics break down completely. The elegant equations of general relativity, which describe gravity so perfectly everywhere else in the universe, produce infinities when applied to this point. An infinity in a physics equation is a red flag. It's a sign to scientists that the theory has been pushed beyond its limits and is no longer providing a sensible answer. It's like trying to use a road map to navigate the middle of the ocean. The map is excellent for what it was designed for, but it has its boundaries. So, what is a singularity, really? The honest answer is that we don't know for sure. It is one of the greatest unsolved mysteries in all of science. It represents the limit of our current knowledge, a place where the two great pillars of modern physics, general relativity, which governs the very large, and quantum mechanics, which governs the very small, must somehow come together. Some theories speculate that it might not be an infinitely small point after all. Perhaps the strange rules of quantum gravity take over at that scale, preventing a true infinity from forming. Maybe it's a quantum foam, a turbulent Planck-scale sea of energy. Or perhaps, as some string theories suggest, it's a fuzzball, a tangled bundle of fundamental strings. More speculative ideas even propose that a singularity could be a gateway to another universe. These are all beautiful, fascinating mathematical possibilities, but at present, we don't have the tools or the theories to test them. The singularity remains hidden from us, forever cloaked behind the one-way mirror of the event horizon. It is the heart of the black hole's mystery, a place where the universe tucks away its deepest secrets in a shroud of infinite gravity, a quiet, humbling reminder that even in a cosmos we can measure and map with incredible precision, there are still places where our science becomes poetry, and our equations give way to silent, reverent wonder. As your imaginary spaceship carries you closer to a black hole, the force of gravity doesn't just get stronger in a simple way, it gets stranger. The immense gravity exerts what are known as tidal forces, and these forces are responsible for one of the most colorfully named and unsettling processes in all of astrophysics: spaghettification. Imagine you are falling feet first toward a black hole. Because your feet are closer to the black hole's center of gravity than your head is, the gravitational pull on your feet is significantly stronger. The difference in that pull from your head to your toes is the tidal force. It's the same kind of force that causes the ocean tides on Earth as the moon pulls more strongly on the side of the Earth facing it than on the side facing away. But near a black hole, this force is magnified to an unimaginable degree. This tidal force would begin to stretch your body vertically. At the same time, because all parts of your body are being pulled toward the single point of the singularity at the center, forces would also be squeezing you from the sides, as if you were in a cosmic vice. The combination of this intense stretching in one direction and compression in the other would draw your body out into a long, thin strand of matter, like a piece of spaghetti being pulled from both ends. It's a bizarre and slightly gruesome thought, but it's a direct and unavoidable consequence of how gravity behaves in extreme environments. For a smaller, stellar mass black hole, these tidal forces are incredibly powerful, even far outside the event horizon. An astronaut falling toward one of these would be spaghettified long before they ever reached the point of no return. Their journey would end in a stream of atoms stretched across the sky. For a supermassive black hole, however, the kind that lies at the center of galaxies, the story is quite different. Because these black holes are so much larger and their event horizons are so much farther out from the singularity, the gravitational curve at the edge is much more gentle. This means that the difference in gravity between your head and your feet would be almost negligible as you cross the event horizon. You could, in theory, drift across the point of no return completely intact, feeling nothing more than a gentle sense of falling. The spaghettification would still be your ultimate fate, but it would occur much later, much closer to the singularity deep inside the black hole's interior, long after you had vanished from the observable universe. This process isn't just a quirky thought experiment. We see evidence of it happening in the cosmos. When a star wanders too close to a supermassive black hole, the tidal forces can rip it apart in an event astronomers call a tidal disruption. The star is stretched and torn into a long, glowing stream of gas. Some of this gas is flung out into space, while the rest spirals into the black hole, creating a bright flare of light that we can detect from millions of light years away. Spaghettification is a stark and powerful reminder of the sheer shaping force of a black hole's gravity. It's not just a passive drain in spacetime, it's an active, sculpting force that can stretch and shred the very fabric of matter, one cosmic strand at a time. One of the most mind-bending and deeply fascinating consequences of gravity's effect on spacetime is how it affects the flow of time itself. According to Einstein's profound insights in his theory of relativity, time is not a universal constant, an unwavering cosmic clock ticking away at the same rate for everyone and everything. Instead, time is relative, and its pace can be stretched or compressed by gravity and by motion. This effect is known as time dilation. The stronger the gravity, the slower time flows. Imagine two friends, each with a perfectly synchronized, hyper-accurate clock. One friend stays safely on Earth, while the other embarks on a journey in a spaceship and goes into a close, stable orbit around a massive black hole. For the friend near the black hole, where gravity is extreme, time would pass much, much more slowly than it does on Earth. After what feels like only a year to them, after they've read a few books and watched a season of their favorite show, they might decide to return to Earth. Upon their arrival, they would find a world transformed. Decades, or perhaps even centuries, could have passed for their friend who stayed behind. The spacefaring friend would be biologically younger. They have literally traveled into Earth's future. This isn't a plot from science fiction. It is a real, measurable effect of the universe we live in. Even here on Earth, time dilation occurs in tiny, almost imperceptible ways. Time ticks ever so slightly slower for someone living at sea level than it does for someone living on top of a high mountain, because gravity is stronger closer to the Earth's massive center. The clocks on the GPS satellites that orbit our planet have to be constantly and carefully adjusted to account for the fact that time moves a fraction of a second faster for them in their high orbit, but where gravity is weaker than it does for us on the ground. Without these relativistic corrections, GPS navigation would fail within minutes. Near a black hole, this effect is taken to its ultimate extreme. As you approach the event horizon, an observer watching you from a safe distance would see your clock ticking slower and slower. Your movements would appear to slow down, and any light you emitted would become redder and dimmer. Eventually, as you reach the very edge, you would seem to freeze entirely, your image forever poised at the brink, a silent, static portrait. For you, however, time would continue to pass perfectly normally. You would feel your own heartbeat at a steady rhythm. The strange part would be looking back at the outside universe. It would appear to speed up dramatically. You could watch stars be born and die, watch galaxies spin and collide in what feels to you like only a few moments. A black hole doesn't just warp space, it warps time, creating a place where a single moment can be stretched into an eternity, and an eon can be compressed into the blink of an eye. It's a place where the steady, familiar river of time, with its past, present, and future, dissolves into the quiet, mysterious ocean of curved spacetime. If black holes are truly black, swallowing all light that comes near them and letting none escape, then how do we possibly find them? It seems like a cosmic paradox, like trying to find a black cat in a coal cellar with the lights off. We find them not by looking for the objects themselves, but by observing their profound and often dramatic effects on the space and matter that surround them. It is a form of cosmic detective work, finding an invisible culprit by the clues it leaves behind. One of the most common and oldest methods is to watch the stars. Many stars in the universe exist in binary systems, gravitationally bound to a companion star, the two orbiting a common center of mass. If one of those stars evolves into a black hole, we can no longer see it directly, but we can still see its visible partner. Astronomers can observe a visible star seemingly orbiting nothing, whipping around an empty point in space at incredible speeds. It's like watching a dancer gracefully twirl around an invisible partner, their movements revealing the phantom presence they are bound to. By carefully measuring the visible star's orbit, its speed, its distance, the shape of its path, they can precisely calculate the mass of its invisible companion. If the calculated mass is more than about 3 times that of our Sun, and it's confined to a tiny, dark region, it's a very strong candidate for a black hole. This stellar dance, this silent orbital ballet, is one of the most compelling pieces of evidence for their existence. Another incredibly powerful clue to a black hole's presence is the phenomenon of the accretion disk. If a black hole has a nearby star, or more commonly, a vast cloud of gas and dust, its immense gravity can begin to pull this material away from its neighbor. This isn't a gentle, straight fall into the abyss. Instead, the material spirals inwards, much like water spiraling down a drain, forming a flat, incredibly hot, and brilliantly glowing disk around the black hole. This disk is the accretion disk, and it is a place of unimaginable violence and energy. The particles in this disk, gas atoms and dust grains, orbit the black hole at tremendous speeds, accelerating closer and closer to the speed of light as they approach the event horizon. Because the inner parts of the disk are moving much, much faster than the outer parts, there is immense friction between the layers of gas. This friction is like rubbing your hands together vigorously to generate heat, but on an unimaginable cosmic scale. It heats the material in the disk to millions, sometimes even billions of degrees. At these extreme temperatures, the gas doesn't just glow with visible light. It emits incredibly powerful high-energy X-rays and gamma rays. These invisible forms of light stream out into the cosmos, making the region around an active black hole one of the brightest objects in the entire universe. In a way, the accretion disk is a black hole's last brilliant farewell to the matter it consumes, a dazzling display of energy before the material slips silently into the perfect darkness of the event horizon. Telescopes specifically designed to detect this high-energy light, like the Chandra X-ray Observatory, can pinpoint these glowing signatures, revealing the presence of a black hole by the dazzling light of its ongoing meal. Sometimes, these accretion disks are so bright that they can outshine entire galaxies, forming what we call quasars, or active galactic nuclei. A single quasar can be 100 times more luminous than our entire Milky Way galaxy, all powered by a supermassive black hole at its core, steadily feeding on the surrounding gas and dust. Beyond the glow of an accretion disk, we can sometimes infer a black hole's presence by the subtle yet profound way its gravity bends the light from objects located directly behind it. This phenomenon is called gravitational lensing, and it's a direct consequence of space-time curvature. Just as a curved lens can distort and magnify images, a black hole with its extreme gravitational pull can act as a powerful cosmic magnifying glass. Imagine a distant galaxy positioned almost perfectly behind a black hole from our perspective on Earth. The light from that galaxy travels toward us, but as it passes the black hole, its path is bent, redirected by the intense gravity. Some light passes slightly above, some slightly below, some to the left, and some to the right. By the time that light reaches our powerful telescopes on Earth, it has been redirected in such a way that the distant galaxy can appear distorted into strange arcs, or magnified to appear brighter than it truly is, or even appear as multiple images surrounding the invisible black hole. If the alignment between the observer, the black hole, and the background galaxy is absolutely perfect, the light from the background galaxy can be stretched and smeared into a complete circle of light, a ghostly halo known as an Einstein ring. It's a beautiful, ethereal sight, a direct visual echo of warped space-time that confirms the presence of the unseen massive object in the foreground. Gravitational lensing is a powerful tool for astronomers, not just for finding black holes, but for studying distant galaxies that would otherwise be too faint to see. It allows us to use these massive cosmic lenses as natural telescopes, peering further into the universe's past. It also provides one of the most direct ways to map the distribution of mass in the universe, including the mysterious dark matter that doesn't emit or reflect light at all. We can only see its gravitational effects, the way it subtly bends light, even if we can't see the matter itself. Each warped image of a distant galaxy, each ghostly Einstein ring, is a silent confirmation of Einstein's theory and a visual testament to the immense invisible power of gravity. It is the universe holding up a lens to its own secrets, allowing us to see the invisible by the gentle, beautiful way it bends the light. For a century, one of the deepest and most astonishing predictions of Einstein's theory of general relativity was that the universe is filled with invisible ripples in the very fabric of space-time. He imagined that just as a heavy-moving boat creates waves in the water, massive, accelerating objects in the cosmos should create waves in space-time itself. These waves, known as gravitational waves, would subtly stretch and squeeze space as they passed by, but the effect would be so incredibly tiny that Einstein himself thought we would never, ever be able to detect them. For decades, gravitational waves remained purely a mathematical concept, a beautiful theoretical possibility. But in 2015, after years of painstaking work and brilliant engineering, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, announced to the world that they had made the first direct detection. The ripples they detected were created by one of the most violent and awe-inspiring events in the universe: the collision and merger of two stellar mass black holes in a distant galaxy over 1 billion years ago. Imagine two heavy stones being dropped into a perfectly still pond. The ripples spread out in concentric circles across the surface. Now, imagine that pond is the entire universe, and the stones are two black holes, each about 30 times the mass of the sun, spiraling into each other at half the speed of light. The waves they create are not in water, but in the very essence of space and time. By the time these incredibly faint waves reached Earth, they were fantastically small, stretching and squeezing our planet by a distance thousands of times smaller than the nucleus of an atom. The LIGO detectors, two of the most sensitive instruments ever built by human hands, were able to measure this tiny, fleeting distortion. The signal they recorded was a faint, almost imperceptible chirp, the sound of space-time itself ringing like an ancient cosmic bell. It started at a low frequency, a quiet hum, and rapidly increased in pitch and volume as the black holes got closer and faster in their final death spiral, ending abruptly at the moment they merged into a single, larger black hole. This detection was a monumental achievement in human history. It opened up a brand new way of observing the universe. For all of recorded history, humanity has studied the cosmos with light, using telescopes that collect everything from radio waves to visible light to gamma rays. Now, for the first time, we could listen to the universe's gravitational symphony. We can hear the silent, majestic collisions of black holes and neutron stars, events that are utterly invisible to traditional light-based telescopes. Each detected gravitational wave carries a rich and complex story about the objects that created it: their precise masses, how fast they were spinning, and the violent, beautiful details of their final dance. It is truly a new sense for humanity, a way to feel the subtle tremors of the cosmos and listen to the silent, profound music of space-time. Black holes, like stars and galaxies, come in different sizes, spanning an enormous range of masses. For a long time, astronomers primarily focused on two main categories because they were the ones for which we had the most direct evidence. First, there are the stellar mass black holes, born from the spectacular collapse of individual massive stars. These are relatively small, typically a few dozen times the mass of our sun. They are the most common type of black hole, scattered throughout galaxies, often quietly orbiting other stars. But at the heart of nearly every large galaxy, including our own spiral home, the Milky Way, lurks a monster of a vastly different scale entirely: a supermassive black hole. These cosmic behemoths can have masses ranging from millions to billions of times that of our sun. They are the undisputed gravitational anchors of their galaxies, holding billions of stars in their immense gravitational embrace. The supermassive black hole at the very center of our Milky Way is named Sagittarius A star, pronounced A star. It has a mass of about 4 million suns, all contained within a region of space smaller than the orbit of Mercury. We can't see it directly, as it doesn't emit light in its current quiescent state, but we have meticulously watched stars orbiting it for decades, like cosmic moths around a silent flame. Their frantic, looping, and incredibly fast paths around the galactic center are undeniable proof of the immense, invisible object they are tethered to. How do these galactic giants form? That question remains one of the most active and exciting areas of research in astrophysics. One leading theory suggests that they started as regular stellar mass black holes in the very early universe, and grew over billions of years by steadily consuming vast amounts of gas, dust, and even entire stars that wandered too close. Another fascinating possibility is that they formed from the direct collapse of immense clouds of gas in the early days of galaxy formation, skipping the stellar phase altogether, falling directly into black hole status. Or perhaps they grew by merging with countless other black holes, building up their mass through innumerable cosmic collisions over eons, like a relentless gravitational snowball. Whatever their exact origin, supermassive black holes play a profoundly crucial role in the evolution of galaxies. Their immense gravity holds the central bulge of stars in place, preventing the galaxy from simply flying apart. The energy and powerful jets blasting out from their active accretion disks can regulate star formation across the entire galaxy, sometimes blowing away the gas needed to form new stars, effectively shutting down star birth, and other times compressing existing gas clouds to trigger new, furious bursts of stellar creation. It's a complex, dynamic feedback loop, a cosmic ecosystem where the central monster and the surrounding galaxy are in a delicate, lifelong dance of creation and destruction. It's humbling to think that as you lie here, listening, your entire solar system, along with hundreds of billions of other stars, is slowly, gracefully orbiting a silent, supermassive black hole 26,000 light years away. It's not a threat to us. It's too far away and too quiet in its current state to affect our little corner of the galaxy. It is simply the gravitational heart of our galactic home, the quiet, heavy anchor that keeps the great spiral of the Milky Way from gently drifting apart in the cosmic dark. For a long time, the black hole family seemed to have a missing link. We had solid evidence for the stellar mass black holes born from individual dying stars and the towering supermassive black holes found at galactic cores. It was like a zoologist discovering only mice and elephants, with no animals in between. But physicists, armed with their equations, predicted that there should be a third class, a middle child, known as intermediate mass black holes, or IMBHs. These would have masses somewhere between 100 and 100,000 times that of our sun, fitting neatly between the small and the large. They are too big to be formed from the collapse of a single star, but not nearly as massive as the supermassive black holes that dominate large galaxies. Finding them, however, has proven to be incredibly difficult. They don't have the brilliant, sustained accretion disks of active supermassive black holes, and they don't always have a visible companion star like many stellar mass black holes do. They are the quiet, elusive middle children of the black hole family, harder to spot in the vastness of space. So, where would they come from? One leading theory suggests that they form in the dense hearts of globular clusters. These are ancient, tightly packed, spherical swarms of hundreds of thousands, sometimes even millions of stars, all orbiting a common center. In such an incredibly crowded environment, stars can collide and merge, and smaller black holes can merge repeatedly, gradually building up into an intermediate mass black hole over time. It's like a cosmic mosh pit where smaller dancers eventually combine to form a larger, heavier entity. Another intriguing idea is that they could be the original seeds of supermassive black holes, the foundational building blocks that later merged and grew to form the galactic giants we observe today. In recent years, evidence for IMBHs has slowly but surely started to emerge. Astronomers have found tantalizing clues in the precise movements of stars within globular clusters, hints of faint gravitational lensing events, and brief, sudden flares of light from stars being torn apart in ways that suggest a mid-sized, unseen culprit. Perhaps the most compelling evidence has come from the detection of gravitational waves. Observatories like LIGO and Virgo have captured the unique gravitational wave signatures from the merger of black holes that fall squarely within the intermediate mass range, giving us our first direct listen to these elusive objects. These IMBHs might represent the missing piece of the puzzle that explains how supermassive black holes grow to such enormous sizes. They could be wandering through galaxies, silently orbiting in the dark, or hiding in the cores of smaller dwarf galaxies, waiting to be discovered. The search for them is like looking for a new species in a vast, dark, cosmic forest. We know mathematically that they should be there, and each faint track, each distant whisper in the gravitational waves brings us closer to understanding the full, rich, and diverse ecosystem of black holes that populates our universe. Most of the black holes we discuss were born from dying stars or grew over billions of years at the centers of galaxies. But there is another, more exotic and profoundly ancient possibility that some black holes were formed in the very first moments of the universe's existence. These are known as primordial black holes. To imagine their creation, we have to travel back in time to the first tiny fraction of a second after the Big Bang. The universe at that unimaginably early stage was an incredibly hot, incredibly dense, and incredibly chaotic place. It was not perfectly uniform and smooth. There were tiny, inherent fluctuations in density from one spot to another, like microscopic wrinkles in the fabric of the nascent cosmos. In regions where the density was particularly high, where matter and energy were just slightly more concentrated, the sheer pressure and gravitational pull could have been enough to cause a direct collapse into a black hole without ever needing to form a star first. It's like a cosmic bubble bursting inward before it even had a chance to expand fully. Unlike their stellar cousins, these primordial black holes could have formed with a huge range of masses, from tiny, almost microscopic sizes to colossal ones. Some might have been as massive as thousands of suns, potentially becoming the initial seeds for the supermassive black holes we observe at galactic cores today. Others could have been incredibly small, perhaps with the mass of an asteroid or even a small mountain, but compressed into a size smaller than a single atom. These mini black holes, if they exist, would be very different from their larger relatives. Because of the subtle phenomenon of Hawking radiation, which we will touch on later, a black hole's evaporation rate is inversely related to its mass. The smaller the black hole, the faster it leaks and eventually disappears. A primordial black hole with the mass of a large mountain would have evaporated over the age of the universe, ending its life in a final, brilliant burst of gamma rays as it winked out of existence. Astronomers have diligently searched for these telltale flashes of light from evaporating primordial black holes, but so far, none have been definitively found, leaving their existence purely in the realm of theory. Nevertheless, primordial black holes remain a fascinating and compelling concept. They have been proposed as a possible candidate for dark matter, the mysterious, invisible substance that makes up about 27% of the universe and whose nature we still don't understand. Perhaps the dark matter we're searching for isn't a new kind of elementary particle, but a vast, silent population of ancient, tiny black holes drifting silently through space, their gravity subtly influencing the galaxies around them. They are echoes of the universe's fiery birth, cosmic seeds scattered in the very first moments of creation. Whether they exist or not remains one of the tantalizing and deepest questions in cosmology. A search for the universe's oldest, most fundamental ghosts in the faint whispers of light from the very dawn of time. For a long time, it was thought that black holes were the ultimate, inescapable prisons of the universe. Once something fell in, it was gone forever, erased completely from existence, its information swallowed and destroyed. This idea created a profound conflict with one of the most fundamental tenets of quantum mechanics, which states that information can never be truly lost or destroyed in the universe. Imagine you burn a book. The information in it, the words, the story, the author's intent, might seem to be gone. But in principle, if you could meticulously collect every single particle of smoke, every tiny bit of ash, and every single photon of light and heat released, a super powerful entity could theoretically reconstruct the original book. The information is just scrambled and dispersed, not utterly annihilated. This is the core principle of information conservation in the quantum world. But black holes, it seemed, violated this sacred rule. When something falls into a black hole, it crosses the event horizon and is irrevocably lost to the outside universe. All of its intrinsic information, what it was made of, its exact quantum state, its precise shape and structure, seems to be irretrievably erased. This creates a deep and troubling paradox between our two best theories of the universe. Einstein's theory of general relativity, which describes the universe on the grandest scales, says the information is trapped inside and gone. Quantum mechanics, which describes the universe on the smallest scales, says information can never be destroyed. This is famously known as the black hole information paradox. For decades, some of the most brilliant minds in physics have wrestled with this fundamental problem. Stephen Hawking's revolutionary discovery of Hawking radiation, which suggested that black holes slowly evaporate, only made the paradox more acute. If a black hole can completely disappear over immense timescales, what happens to the information of all the things that fell into it? Does it simply vanish from the universe, utterly violating the laws of quantum physics? Or is it somehow encoded subtly and mysteriously in the faint, random particles of Hawking radiation that slowly leak out? One popular and mind-bending idea, known as the holographic principle, suggests a potential solution. It proposes that all the information about what has fallen into a black hole isn't actually stored inside the three-dimensional volume of the black hole. Instead, it is theorized to be stored on the two-dimensional surface of its event horizon, like a cosmic hologram. When the black hole slowly evaporates through Hawking radiation, this information is somehow slowly and subtly imprinted onto the outgoing particles, preserving it. It's a truly mind-bending concept, suggesting that our entire three-dimensional reality might, in some profound sense, be a projection of information stored on a distant two-dimensional surface, much like a 3D movie is projected from a 2D film reel. The information paradox is still unsolved, a persistent challenge at the very frontier of our understanding. It sits at a profound crossroads where gravity and quantum mechanics meet and for now refuse to agree. It's a cosmic puzzle that hints at a deeper, more profound theory of reality still waiting to be discovered, a grand unified theory that can reconcile these two pillars of physics. It's like a library where the books have been burned and we are trying to read the stories in the faint lingering patterns of the smoke, a testament to the universe's most subtle secrets. In the elegant world of theoretical physics, for almost every concept there often seems to be a theoretical opposite, a kind of mirror image. For a black hole, an object defined by its relentless, inescapable inward pull, only letting matter and energy in, its theoretical counterpart is a white hole. An object that, if it existed, would only ever let matter and energy out. If a black hole is the ultimate cosmic drain, pulling everything into its silent abyss, a white hole would be a cosmic spring, a place from which matter and energy spontaneously and continuously emerge, relentlessly spewing out into the universe. Imagine trying to approach a white hole. You would find it utterly impossible to enter. It would repel all incoming matter and light, like a cosmic force field, pushing everything away. The idea of a white hole comes directly from the same mathematical solutions of Einstein's theory of general relativity that predict black holes. The equations of general relativity are time-symmetric, meaning they work just as well if you run them backward in time as they do if you run them forward. A black hole is a solution where matter collapses inward to a singularity in the future. If you take that solution and simply run it backward in time, you get a white hole, a singularity in the past from which matter and energy continuously emerge into the future. It's a perfect mathematical reversal, a cosmic fountain to the black hole's drain. While they are a perfectly valid mathematical solution, most physicists believe that white holes don't actually exist in our universe. Their theoretical existence would seem to violate some fundamental physical laws and common observations, such as the second law of thermodynamics, which states that entropy, or disorder, in a closed system almost always increases over time. A white hole would be a source of immense energy and highly structured matter spontaneously emerging from nothing, representing a decrease in entropy that nature, as we understand it, seems to forbid. There's also no known astrophysical process that could realistically create a white hole. They remain beautiful mathematical ghosts, intriguing theoretical constructs that remind us that the equations describing our universe can sometimes imagine possibilities that nature, for its own deep and complex reasons, chooses not to build. They are the cosmic road not taken, a quiet whisper of what could be in a universe defined by what truly is. They exist in the abstract beauty of equations, a testament to the boundless imagination of mathematics itself. If a black hole is a doorway in and a white hole is a doorway out, it's only natural to wonder if you could connect the two, creating a shortcut through the vastness of space and time. This is the simple yet profoundly complex idea behind a wormhole. Imagine space-time as a giant, perfectly flat sheet of paper. You want to get from a point on one side of the paper to a point on the other, a journey that would take an incredibly long time if you just crawled across the surface. But what if you could fold the paper over, bringing the two distant points very close together? Then you could simply poke a pencil straight through the folded paper, like creating a tunnel that connects them directly. This theoretical tunnel through space-time is what physicists call an Einstein-Rosen bridge, or more famously, a wormhole. It's conceived as a shortcut, a potential connection between two very distant points in our own universe, or perhaps even a bridge to an entirely different universe altogether. In theory, the mouth of the wormhole on one end could be a black hole, pulling matter in, and the mouth on the other end could be a white hole, expelling it somewhere else instantly. You would fall into the black hole, travel through the incredibly narrow and unstable throat of the wormhole, and emerge from the white hole thousands, millions, or even billions of light years away, or perhaps into a parallel reality. It's a concept that has fueled science fiction for decades, inspiring countless stories of interstellar travel and alternate dimensions. But there's a significant catch, and it's a big one. According to our current understanding of physics, these wormholes, if they could ever form, would be incredibly unstable. The throat of the wormhole would likely collapse back into a singularity the instant it formed, faster than even light could possibly travel through it. To keep such a wormhole open and traversable, you would need some kind of exotic matter with incredibly strange properties, such as negative energy density or negative pressure. This is a form of matter we have never observed and don't know how to create. It's not just antimatter, but something even more unusual, a substance that would exert a repulsive gravitational force, pushing the wormhole open from within. So for now, wormholes remain firmly on the theoretical blackboard and in the captivating realm of our imaginations. They are a beautiful what if, a compelling dream of cosmic shortcuts woven from the same mathematical fabric as the black holes we know are real, but a dream that seems, for now, beyond the reach of our current physics. They are a reminder that the universe might contain geometries even stranger than we can currently prove, and that our understanding is still evolving, always pushing the boundaries of what's possible. Imagine a person with a truly unique and distinctive appearance. Intricate, perhaps wild, hair, incredibly detailed clothing, and a deeply individual, complex personality. Now imagine that this person walks into a room, and when they emerge, they have been transformed into a perfectly smooth, completely featureless sphere. All of their complex individuality, all their intricate details, their unique identity have been utterly wiped away. This is, in a profound and somewhat playful sense, what happens to matter that falls into a black hole, according to a principle known as the no-hair theorem. The name is indeed a bit playful, a touch of physics humor, a nod to the loss of distinguishing characteristics. But the idea behind it is incredibly profound and speaks to the ultimate simplicity of these cosmic giants. The no-hair theorem states that once a black hole settles down into a stable state, whether after its initial formation from a collapsing star or after consuming additional matter, it can be completely described by only three fundamental physical properties: its total mass, its spin, meaning how fast it's rotating, and its net electric charge. That's it. All the other hair, all the other complex information about what it was made of, whether it was a blue giant star or a red dwarf star, a planet made of rock or a cloud of hydrogen gas, its magnetic field, its internal composition, its quantum state, is considered lost to the outside universe. From the perspective of an external observer, you can't tell the difference between a black hole formed from a collapsed star and one formed from 1 trillion tons of collapsed armchairs, as long as their final mass, spin, and charge are identical. It is the universe's ultimate form of information compression, a cosmic reset button. No matter how complex and varied the ingredients that fall in, the final result is always the same: elegant, simple, gravitationally pure object. This theorem has been a cornerstone of black hole physics for decades, simplifying how we think about these complex objects. While the information paradox we discussed earlier challenges the ultimate fate of that lost information, The no-hair theorem still powerfully describes how black holes appear to us from the outside. It speaks to the profound power of gravity to smooth over all details, to erase individual histories, and to present a face to the universe that is defined only by its most fundamental, irreducible properties. It's a quiet testament to the idea that in the most extreme and powerful places in the cosmos, complexity can give way to a kind of perfect, featureless calm, a silent, cosmic purity. Imagine a roaring bonfire on a bitterly cold night. It burns brightly for a time, a vibrant source of warmth and light in the encompassing darkness, crackling and spitting with energy. But eventually the wood is consumed, the flames die down, and the embers slowly fade to a dull gray ash, leaving behind only a lingering coolness in the air. The universe, on a scale that defies human comprehension, will likely follow a similar, albeit vastly slower path. And black holes, ironically, are destined to be the main characters in its final, incredibly long act. In the unimaginably far, far distant future, trillions upon trillions of years from now, long after all the stars in the universe have burned out their nuclear fuel and faded, the universe will have expanded and cooled to an extreme degree. It will enter what physicists call the degenerate era, or the dark era. It will be a cold, dark, and incredibly quiet place, populated only by the cold, inert remnants of stars, white dwarfs, neutron stars, and the remaining black holes. The black holes will be the last major players on this immense cosmic stage. They will continue to slowly sweep up the remaining stray dust, gas, and stellar corpses, gradually growing ever so slightly in the profound silence. But even these ultimate gravitational prisons are not eternal. Thanks to the groundbreaking work of Stephen Hawking and his theory of Hawking radiation, we now understand that black holes are not perfectly black. They should, in fact, very, very slowly radiate away their mass and energy. The process is incredibly slow. For a black hole with the mass of our sun, it would take far, far longer than the current age of the universe, which is about 13.8 billion years, to evaporate even a tiny fraction of its mass, like a single atom's worth. For a supermassive black hole with masses billions of times that of the sun, the process is even slower still. They currently gain more mass from stray gas and cosmic background radiation than they lose to Hawking radiation, so they are still growing. But the theory implies that in the extremely far, far distant future, when the universe is truly cold and dark and all other forms of matter have decayed, black holes will be the last objects to remain, and even they, patiently and silently, will eventually fade away. They will slowly radiate their mass back into the vast emptiness of the universe as a faint trickle of particles until one by one they disappear, perhaps ending in a final, quiet pop of energy. It is a profound and perhaps somber thought, but also a strangely peaceful one. It speaks of a universe returning to a state of ultimate equilibrium, its grand story told, its great cosmic fires extinguished, settling into an endless, uniform, silent night. Black holes are not just the ghosts of dead stars. They are, in a profound sense, the ultimate embers of the universe itself, the last warm things to fade in the eventual, eternal, cool stillness of time. Their slow disappearance is the universe's final act of returning all that it has gathered back into nothingness. Beyond the well-understood realms of stellar and supermassive black holes and the theoretical whispers of primordial ones, the universe holds even more exotic possibilities when it comes to these gravitational singularities. One such theoretical entity is the naked singularity. In all our discussions so far, we've talked about the event horizon as the point of no return, the invisible boundary that shrouds the singularity from our view. The event horizon acts like a one-way screen, keeping the weirdness of the singularity safely hidden from the rest of the universe. This concept, that every singularity is cloaked by an event horizon, is known as cosmic censorship. It's a hypothesis that suggests nature somehow prevents singularities from being naked, meaning exposed to the outside world. If a naked singularity existed, it would be a true breakdown of physics as we know it. Imagine being able to see a point of infinite density with your own eyes, able to interact with it, perhaps even manipulate it. All the paradoxes of the singularity, infinite curvature, breakdown of predictability, would be laid bare for the entire universe to observe and potentially be affected by. It would be a place where the laws of physics could be broken, where cause and effect might cease to function in a predictable way. For example, if you could send a signal into a naked singularity and it emerged with a different outcome than expected, it could potentially allow for time travel paradoxes or instantaneous information transfer. Most physicists believe that cosmic censorship holds true, that naked singularities are either impossible or incredibly short-lived, unstable anomalies. The equations allow for them under very specific, perhaps unrealistic conditions, such as the collapse of a star that is perfectly infinitesimally symmetrical and rotating at an extreme precise speed. But any slight deviation, any tiny imperfection, would likely cause an event horizon to form, thus cloaking the singularity. The idea of a naked singularity is both terrifying and exhilarating to physicists. It's a boundary condition, a theoretical line that, if crossed, would fundamentally change our understanding of how the universe works. It's a reminder that even our most robust theories have their edge cases, their theoretical monsters that, thankfully, nature seems to prefer to keep hidden behind a veil of space and time. It is the universe's ultimate secret, safely tucked away where its strange properties cannot disrupt the orderly flow of reality we experience. As you drift deeper into calm, let's consider another fascinating aspect of black holes, their potential for interaction and feeding. While black holes are often portrayed as silent, solitary cosmic vacuums, they are in fact dynamic objects that interact with their environment in dramatic ways. We've already touched on accretion disks, where gas and dust spiral in, heating up and glowing. But what about when a black hole actively eats something substantial, like a star? When a star wanders too close to a black hole, the outcome is rarely gentle. For a stellar mass black hole, if a star gets too close, it can be completely engulfed, swallowed whole. But for supermassive black holes, the tidal forces can rip the star apart before it even reaches the event horizon. This is a tidal disruption event, and it's a truly spectacular cosmic phenomenon. Imagine a star, perhaps like our sun, happily living its life, and then it gets too close to the immense gravity of a supermassive black hole. The side of the star closer to the black hole experiences a much stronger gravitational pull than the side facing away. This differential force stretches the star into a long, thin stream of gas, like a giant cosmic noodle. This process is aptly named spaghettification, as we discussed earlier. As this stellar spaghetti spirals around the black hole, the friction and compression heat the gas to incredible temperatures, causing it to flare brightly in X-rays and other forms of radiation. This sudden, brilliant flash of light can be observed by our telescopes for weeks or even months, an unmistakable signature of a black hole's meal. It's a violent, cataclysmic event, but it provides invaluable data for astronomers, allowing them to study the black hole itself and the physics of extreme gravity. These events also play a role in the growth of supermassive black holes, as the consumed stellar material adds to their immense mass. Not all of the shredded star falls into the black hole. Some of the gas, superheated and accelerated to incredible speeds, can be blasted back out into space in powerful jets or outflows, enriching the interstellar medium with heavier elements. These events are not just cosmic spectacles. They are fundamental processes in galaxy evolution, shaping the distribution of gas and dust and even influencing the rate of star formation. A black hole's feeding habits are a testament to its immense gravitational power, a quiet, irresistible force that can shred and consume even the mightiest stars, turning their fiery existence into a final brilliant burst of light before they join the silent darkness within. It's a cosmic cycle of destruction and redistribution, shaping the universe one dramatic meal at a time. As we journey further into the mysteries, let's consider the concept of black hole evaporation, a truly mind-bending idea that connects the largest objects in the universe with the smallest, most fundamental particles. For a long time, black holes were thought to be eternal, permanent fixtures that would last forever, trapping everything within them without end. But in 1974, Stephen Hawking, blending the theories of general relativity, which describes gravity and the very large, and quantum mechanics, which describes the very small particles, proposed something truly revolutionary. Black holes are not perfectly black. Instead, they should slowly, painstakingly, and faintly glow, emitting a trickle of particles and radiation that eventually leads to their complete disappearance. This emission is now famously known as Hawking radiation. To understand this, we need to take a brief, calming dip into the strange world of quantum physics. In the quantum realm, empty space is not truly empty and still. It's a bubbling, fizzing, seething sea of virtual particles that are constantly popping into existence in pairs. A particle and its corresponding antiparticle, and then almost instantly annihilating each other, vanishing back into nothingness. It's a constant, quiet hum of creation and destruction, a cosmic dance happening everywhere, all the time, even in what we perceive as a vacuum. Hawking realized that if one of these virtual particle pairs happened to appear right at the very edge of a black hole's event horizon, a peculiar thing could occur. It's possible that one particle of the pair could fall into the black hole while its partner escapes into space. From an outsider's perspective, it would appear as if the black hole had just spontaneously emitted a particle. Because of the fundamental laws of energy conservation, the particle that escapes carries away a tiny amount of energy, and this energy must, by cosmic law, come from the black hole itself. According to Einstein's famous equation, E=mc quasi, mass and energy are equivalent. So if the black hole is slowly losing energy, it must also be slowly losing mass. This means that black holes, contrary to earlier belief, are not eternal. They should very, very slowly evaporate over immense timescales, gradually shrinking and fading away. The process is incredibly slow for most black holes. For a black hole with the mass of our sun, it would take an unimaginable amount of time, longer than the current age of the universe by many orders of magnitude, to evaporate even a single atom's worth of mass. For a supermassive black hole, the process is even slower still. They are currently growing by taking in more mass from stray gas and cosmic background radiation than they lose to Hawking radiation. So they are still very much active giants. But the theory implies that in the unimaginably far, far distant future, when the universe is cold and dark and all the stars have long since burned out, black holes will be the last objects to remain. And even they, patiently and silently, will eventually fade away, with slowly radiating their immense mass back into the vast emptiness of the universe until nothing is left. Hawking radiation is a beautiful, profound, and deeply unsettling idea. It suggests that even the ultimate prisons of the cosmos eventually leak, slowly returning what they have taken in a faint, final whisper. It is a powerful reminder that nothing, not even a black hole, is truly eternal, and that the universe is always, always subtly changing, even in its deepest and darkest corners. Black holes are often imagined as solitary cosmic monsters, isolated in the vastness of space, but in reality, they are part of a dynamic and interconnected universe, often interacting with other celestial bodies in complex ways. We've talked about how they feed on stars and gas, creating accretion disks, but sometimes black holes come much, much closer. They can form binary systems with other stars or even with other black holes. Imagine two dancers bound together by an invisible, powerful force, spiraling around each other in an increasingly frantic waltz. This is the celestial dance of binary black hole systems. When two black holes orbit each other, they constantly disturb the fabric of space-time, creating gravitational waves that ripple outwards, much like two heavy rocks thrown into a pond. As they emit these gravitational waves, they slowly lose energy, causing them to spiral closer and closer together, their dance becoming more and more intense. This is a gradual process taking billions of years, but eventually, in the final moments of their cosmic waltz, they reach astonishing speeds, circling each other at a significant fraction of the speed of light. In these last milliseconds, the gravitational wave emission becomes incredibly powerful, creating a burst of ripples that our LIGO and Virgo detectors on Earth can pick up as that characteristic chirp sound. Then, in a final, cataclysmic embrace, the two black holes merge into a single, larger black hole. This merger is one of the most energetic events in the universe, releasing more energy in that fleeting moment than all the stars in the observable universe combined. It is a silent explosion of space-time itself, a profound cosmic reverberation that echoes across light years. These mergers are not just theoretical, they are what LIGO and Virgo have been detecting, opening up a new window into the universe. Each detected merger event tells us not only that binary black holes exist, but also provides crucial information about their masses, their spins, and how they evolve. The study of these binary systems helps us understand how galaxies grow, how supermassive black holes form through mergers, and even how the very fabric of spacetime behaves under the most extreme conditions imaginable. It's a testament to the fact that even the most solitary objects in the cosmos are, in their own powerful way, deeply interconnected, constantly influencing each other in a silent, gravitational symphony. It is a dance that began in the cosmic past and continues to unfold, leaving its beautiful, invisible marks across the universe. As we settle deeper into the quiet, let's consider a question that has long intrigued scientists and captured the imagination of storytellers. What would it really be like to fall into a black hole? Of course, this is a thought experiment, a journey we take only in our minds, as no human could survive the journey to even a stellar mass black hole. Let's imagine a highly advanced, indestructible probe, equipped with sensors, falling toward a black hole. As the probe approaches, time dilation would become apparent. From the perspective of a distant observer, the probe would appear to slow down as it gets closer to the event horizon, its clock ticking more and more slowly, its light reddening. It would seem to hover indefinitely at the edge, an infinitely stretched moment. But for the probe itself, its internal clock would continue to tick normally. It would not feel any special sensation as it crosses the event horizon. There's no physical barrier, no alarm bell, no sudden jolt. It's simply the point where escape becomes impossible. Once inside, however, the real strangeness would begin. The concept of inside a black hole is very different from any other place in the universe. Inside the event horizon, space and time effectively swap roles. Instead of space being something you move through to reach a destination, and time being a steady progression, time itself becomes the direction you are pulled. You cannot stand still in time, just as you cannot stand still in space inside a black hole. Every path, every direction inevitably leads you towards the singularity. It's like being on a perfectly smooth, infinitely steep downhill slope, where no matter which way you turn, the only direction is down. The gravitational forces would become increasingly extreme. As we discussed, for a smaller black hole, spaghettification would quickly stretch the probe into a long, thin stream of atoms, long before it even reached the singularity. For a supermassive black hole, the stretching forces would be less intense at the event horizon, allowing the probe to cross intact. But as it plunged deeper, the differential gravity would intensify, eventually tearing the probe apart as it hurtled toward the singularity. The light from the outside universe would appear to blue shift and compress as the probe falls, and then vanish entirely as the event horizon closes off the view. The experience would be one of irreversible, accelerating descent into infinite darkness. What happens at the singularity remains unknown, a point where our physics breaks down. The journey into a black hole is a one-way trip, a plunge into the unknown. It is a cosmic illustration of ultimate commitment, a journey from which no information, no light, and no Voyager ever returns, a profound testament to the power of pure gravity. As we consider the grand tapestry of black holes, it's worth taking a moment to appreciate the fascinating, sometimes unexpected ways they can influence their galactic homes. Black holes are not just passive drains in space. They are active, dynamic forces that profoundly shape the evolution of the galaxies in which they reside. This relationship is a complex feedback loop, a cosmic conversation between the central monster and the billions of stars around it. Supermassive black holes at the centers of galaxies are often referred to as active galactic nuclei, or AGN, when they are actively feeding. As gas and dust spiral into their accretion disks, they emit immense amounts of energy, not just in X-rays, but across the entire electromagnetic spectrum. This energy, sometimes channeled into powerful jets that blast out from the black hole's poles, can have a dramatic impact on the surrounding galaxy. Imagine a huge cosmic fan blowing away the raw materials needed for star formation. These powerful outflows and jets can sweep away vast clouds of cold gas and dust, essentially sterilizing regions of the galaxy and preventing new stars from being born. This process is called quasar feedback, or AGN feedback, and it's thought to be a crucial mechanism by which galaxies stop forming new stars and become red and dead elliptical galaxies, made mostly of old stars. But the influence isn't always destructive. Sometimes the jets and outflows can compress existing clouds of gas, triggering new bursts of star formation in other regions of the galaxy. It's like a cosmic gardener, selectively pruning and encouraging growth in different parts of the galactic garden. The mass of the central supermassive black hole is also remarkably correlated with the properties of its host galaxy, particularly the mass of the galaxy's central bulge of stars. This M-sigma relation suggests that the black hole and its host galaxy somehow co-evolved, growing together over billions of years. It's not clear which came first, the massive black hole or the galaxy, or if they grew in tandem, constantly influencing each other's development. Perhaps the black hole's gravity acted as a seed for galaxy formation, or perhaps the immense amount of gas in early galaxies provided the fuel for the black holes to grow rapidly. These are still open questions, but the strong correlation hints at a deep and intimate connection. The influence of black holes extends far beyond their immediate vicinity. They are the silent gravitational conductors of galactic evolution, orchestrating the birth and death of stars, shaping the very structure of their home galaxies, and leaving their indelible mark on the cosmic landscape. It's a powerful reminder that even the most seemingly destructive forces in the universe play a vital, creative role in its grand unfolding story. For years, black holes were mostly theoretical constructs, existing brilliantly in Einstein's equations but lacking direct observational proof. The turning point came with the development of sophisticated telescopes and observational techniques, allowing us to move from inference to actual seeing. The most iconic example of this is the Event Horizon Telescope, or EHT. Imagine trying to take a picture of a grapefruit on the moon. It's an impossible task for a single telescope. But what if you could link together radio telescopes from all over the world, from Hawaii to Chile, from Spain to the South Pole, forming a virtual telescope the size of Earth? That's what the EHT accomplished. Their target was Sagittarius A Sti, the supermassive black hole at the center of our Milky Way, and later the black hole at the center of the galaxy M87. For Sagittarius A Sti, taking the picture was like trying to photograph a donut-sized object on the moon from Earth through a blurry atmosphere. But the EHT was not trying to photograph the black hole itself, which is by definition invisible. Instead, they aimed to capture the image of the superheated glowing gas and plasma swirling just outside the event horizon. This gas is so hot it emits radio waves, which can penetrate the dust and gas clouds that obscure our galactic center. In 2019, the EHT released the first ever image of a black hole, specifically the one in M887. It wasn't a solid object, but a luminous ring of light, a fiery halo surrounding a central region of perfect darkness. This dark region, roughly circular, was the shadow of the black hole, cast by the warped spacetime around the event horizon. It was a stunning confirmation of Einstein's predictions and a monumental achievement in observational astronomy. The light in the ring is from the superheated accretion disk, glowing just before it plunges into the black hole. The asymmetry in the ring, with one side appearing brighter, is due to relativistic beaming and Doppler effects. The gas moving toward us appears brighter, while the gas moving away appears dimmer. The image isn't a perfect photograph in the traditional sense. It's a computational reconstruction from petabytes of data collected by the global array of telescopes. But it provides irrefutable visual evidence of a black hole's presence and the extreme conditions around it. This image didn't just confirm theories. It gave us a face for these cosmic enigmas, transforming them from abstract mathematical concepts into tangible, albeit terrifyingly powerful, realities. It was a silent, luminous portrait of ultimate darkness, a testament to humanity's relentless curiosity and our ability to see the unseen. As we continue this calm journey through the cosmic night, let's explore some of the more speculative yet incredibly tantalizing ideas connected to black holes. One such idea is the possibility of them acting as engines for cosmic rays. Cosmic rays are incredibly high-energy particles, mostly protons and atomic nuclei, that constantly barred Earth from outer space. They travel at nearly the speed of light and carry far more energy than any particle we can produce in our largest accelerators on Earth. Where do they come from? That's one of astronomy's enduring mysteries. While supernovas are thought to be one source, they can't explain the very highest energy cosmic rays. This is where black holes enter the picture. Particularly active galactic nuclei, AGN, which are supermassive black holes furiously feeding at the centers of galaxies, are prime candidates. As matter falls into an AGN's accretion disk, immense magnetic fields are generated and twisted by the rapidly rotating, highly charged plasma. These magnetic fields can act like powerful cosmic particle accelerators. Imagine a giant, invisible slingshot. Particles caught in these swirling, energetic magnetic fields can be accelerated to incredible speeds, approaching the speed of light, and then flung out into space as cosmic rays. These particles can then travel across vast intergalactic distances, eventually reaching our solar system. The jets that blast out from AGNs are thought to be particularly efficient at this. These collimated beams of matter and energy are essentially giant particle accelerators, extending for thousands or even millions of light years. The extreme conditions near the black hole, the intense gravitational gradients, the powerful magnetic fields, and the incredible friction within the accretion disk all contribute to creating an environment where particles can gain such phenomenal energies. The connection between black holes and cosmic rays is still an active area of research. Detecting these ultra-high energy particles and tracing them back to their origin is incredibly challenging, as their paths are bent by galactic magnetic fields, obscuring their source. But the theory provides a compelling explanation for some of the most energetic phenomena in the universe. It suggests that black holes, even as they consume matter, are also powerful engines of creation, indirectly shaping the cosmic landscape by flinging these high-energy messengers across the vastness of space. It's a reminder that nothing in the universe is truly isolated. Even the darkest objects are constantly influencing the broader cosmos, a silent, powerful pulse in the night. Let's now turn our attention to the fascinating idea of black hole thermodynamics, a field that beautifully marries the physics of gravity with the laws of heat and energy, adding another layer of quiet complexity to these cosmic enigmas. For a long time, black holes were thought to be perfect absorbers, violating the second law of thermodynamics, which states that entropy, a measure of disorder, always increases or stays the same in an isolated system. If you could drop something with low entropy, like a neatly organized book, into a black hole and it disappeared forever, it would seem like the universe's overall entropy had decreased, which is a big problem for physics. However, Stephen Hawking's discovery of Hawking radiation provided a profound solution. If black holes actually emit radiation, it means they have a temperature. And if they have a temperature, they must also have entropy. This was a revolutionary concept, that an object defined by its lack of observable features could possess thermodynamic properties. The entropy of a black hole turns out to be proportional to the surface area of its event horizon. The larger the event horizon, the more disorganized information it contains. This connection between geometry, area, and information entropy is one of the deepest insights in physics, hinting at a holographic nature of reality, as we briefly discussed earlier. It's like saying that the messiness of your room is not about what's inside, but how much floor space it takes up. When something falls into a black hole, its entropy is essentially transferred to the black hole's entropy, so the total entropy of the universe still increases or stays the same. The second law of thermodynamics is saved. This field of black hole thermodynamics also leads to the concept of the generalized second law of thermodynamics, which states that the sum of the entropy of black holes and the ordinary entropy of matter and radiation outside black holes never decreases. It's a way of looking at the universe's ultimate fate, suggesting a slow, gradual increase in total cosmic disorder, with black holes being key players in that final, quiet dispersal of energy and information. This connection between gravity, quantum mechanics, and thermodynamics is a beautiful example of how seemingly disparate areas of physics are deeply intertwined, revealing a profound and elegant order beneath the chaotic surface of the universe. It's a testament to the universe's own intricate bookkeeping, a silent, cosmic ledger where no energy, no information, and no disorder is ever truly lost. As we journey through these cosmic wonders, it's worth taking a moment to appreciate the humble beginnings of our understanding. The concept of something so dense that even light couldn't escape actually predates Einstein's complex theories of relativity. The first inklings of what we now call a black hole emerged from the minds of 18th century scientists long before the terms space-time or event horizon were ever conceived. In 1783, an English clergyman and amateur astronomer named John Michell presented a paper to the Royal Society of London. He mused about the properties of a hypothetical star so massive and so compact that its escape velocity, the speed needed to escape its gravitational pull, would exceed the speed of light. Light, at the time, was thought to be made of particles, corpuscles, and Michell simply applied Newton's laws of gravity to these particles. He calculated that if the radius of a star with the density of the sun were more than 500 times that of the sun, its surface gravity would be so strong that light itself would be pulled back. He called these objects dark stars. A few years later, in 1796, the brilliant French mathematician Pierre-Simon Laplace independently arrived at a similar conclusion. He described how it was possible that the greatest luminaries in the universe may, through this cause, be invisible to us. These early ideas were remarkably prescient, even though they were based on classical Newtonian physics, which doesn't fully account for the behavior of light and gravity at extreme speeds and densities. They understood the core concept, immense gravity trapping light. However, their ideas were largely forgotten for over a century, seen as curious mathematical oddities rather than descriptions of real cosmic objects. It wasn't until Einstein developed his general theory of relativity in the early 20th century that the true relativistic nature of these dark stars could be understood. Michell and Laplace didn't conceive of space-time curving or of a point of no return. But their pioneering work laid the conceptual groundwork, quietly whispering about the existence of these strange, light-trapping entities. It's a beautiful example of how scientific progress often builds slowly, with earlier thinkers planting seeds that only flourish much later, once the right theoretical soil and observational tools emerge. The story of black holes, then, is not just a tale of modern physics, but a quiet echo from the Enlightenment, a testament to the enduring power of human curiosity stretching across centuries. Finally, as we come to the end of this gentle journey through the cosmos on the profound implications of black holes for our understanding of the universe, and indeed, ourselves. Black holes, these dark, silent gravitational anchors, are more than just cosmic oddities. They represent the ultimate testbeds for our theories of physics, pushing the boundaries of general relativity and forcing us to confront the deepest mysteries of quantum mechanics. They are places where space and time warp in unimaginable ways, where the familiar rules of causality might fray at the edges, and where information itself battles for its survival. From the earliest musings of Michell and Laplace to the direct imaging by the Event Horizon Telescope and the subtle chirps detected by LIGO, our journey of understanding has been long and arduous, but incredibly rewarding. These objects are the ultimate proof of Einstein's genius, the most extreme manifestation of gravity's power. They are the silent architects of galactic evolution, shaping the birth and death of stars, influencing the very structure of the universe around them. But beyond the science, black holes offer us a unique perspective on our place in the cosmos. They are a constant, quiet reminder of the vastness of the unknown, the humbling limits of our current knowledge, and the endless potential for discovery that still lies ahead. When you gaze up at the night sky, you are not just seeing stars and galaxies. You are seeing the silent, invisible gravitational dance of black holes, their immense presence subtly shaping the light and matter all around them. The elements that make up your body, the carbon, the oxygen, the iron, were forged in the heart of stars that lived and died, sometimes collapsing into these very black holes. You are, in a profound sense, made of star stuff that once danced near the edges of these cosmic giants. So, as we come to the end of this journey through the universe's darkest secrets, I hope you've felt the wonder that lies beneath the surface of the everyday and the deep, silent beauty of physics. I hope this has been interesting, but not so interesting that it kept you from resting. And if it did keep you awake, well, at least you've learned something new about the world, about the cosmos, and maybe about yourself before you drift off. If you're still peacefully listening with your eyes closed, I'd love to know. Where in the world are you tuning in from? What time is it where you are? Are you curled up in bed under soft blankets or on the couch with a pet? Are you hearing the hush of night outside your window or the quiet hum of a distant city? Let me know in the comments. I love hearing where this sleepy science has taken you. And if you enjoyed this exploration, if you found it relaxing, interesting, or gently thought-provoking, please consider giving this video a like or subscribing to the channel. It helps me bring more of this content to you, and it lets me know that these gentle dives into science are bringing a little more wonder into the world. Thank you so much for being here and for joining me in this quiet celebration of how the universe works, one invisible gravitational pull at a time. And remember, even when nothing seems to be happening, the universe is still turning, space-time is still curving, and the story of the cosmos is still quietly, beautifully unfolding.